Welcome everyone. Good afternoon, good morning, good evening, wherever you're tuning in from, and welcome to Pixxel's third webinar on the hyperspectral advantage in agriculture. My name is Amy Zammit, and I form part of Pixxel's marketing team, and I'll be moderating today's session, where my colleagues will share some insights into hyperspectral imagery's applications in agriculture. You can jump to the next slide. So, just to give a bit of a background on Pixxel and what we do. Pixxel is a space data company building a constellation of the world's highest resolution Earth imaging satellites and the analytical tools to extract insights from this data. The constellation, once up in space, will measure vital indicators of planetary health and provide daily global coverage to detect, monitor, and predict key phenomena and threats. Upon completion, the constellation will support a diverse range of applications across several use cases and industries. For instance, in agriculture, it will help to assess several vital parameters, including crop and soil conditions, track carbon-related applications, identify diseases, and enhance our understanding of crop physiology and phenology. As core company values, Pixxel is deeply committed to leading the charge of climate technology and sustainability by paving the way for a healthier and more resilient planet through building a health monitor for our planet Earth. Today, I'm joined by my colleagues, Jimmy Greco, who's Pixxel's sales director for North America. Jimmy has diverse experience in sales processes in the geospatial sector and specializes in creating data solutions using this imagery. Within the webinar, he'll be sharing some insights into Pixxel's missions and giving context to the hyperspectral applications within the agricultural sector. We're also joined by Megan Gallagher, our senior solutions engineer, who holds a lot of experience in modalities of geospatial engineering. Megan will be showcasing some real-world applications of hyperspectral imagery through various exhibits and use cases performed on our very own hyperspectral imagery. Just a quick note before we begin, you'll notice that you've all been put on mute to ensure that there are no interruptions throughout the session. However, we will keep the Q&A box open throughout, and towards the end of the session, we'll have a 10-minute Q&A to be able to answer your questions. However, since we're a bit short on time, if there's any unanswered questions, we'll reach out to you via email. Also, the webinar is being recorded and will be available on demand at a later date. So now to begin the session, I'll hand it over to Jimmy Greco. Thanks.
Thank you, Amy. And welcome everybody. Thanks again for hopping on to Pixxel's agricultural webinar today. As Amy said, I'm Jimmy Greco, the sales director here of Pixxel of North America. And today we're going to be talking about our hyperspectral constellation in regards to agriculture and what Pixxel is trying to do. And our mission and what we have begun to do is create the world's first hyperspectral constellation. And what we've seen is kind of there's been this lack of ability or accessibility for hyperspectral constellations for a commercial use. So we've gone ahead and created this constellation that will have a global coverage, so able to access all parts of the world on a daily cadence. And this allows for up to 50 times more information than what's currently available from our other commercial satellites. And these satellites will have a hyperspectral resolution that has not been seen before. So these will have 5-meter spatial resolutions with over 250 bands within the V-SWIR range. And this will allow people to kind of start to utilize hyperspectral in a way that hasn't been available before, given its accessibility and affordability to everybody. Next slide, please. So in terms of our flight path and kind of our roadmap, we've already launched 3 tech demonstrators. We call them our tech satellites. And these were essentially different iterations of the camera that we have on our constellation that is launching later this year. And what we've done with those tech demonstrators is we've used our 50 early adopter people that are joined with us, and then our 80 partners to kind of start to test in the different use cases that are available and start to figure out kind of what are the best applications for these satellites and to understand that moving forward as we move into our commercial constellation. Later this year, we are sending up 6 of our Firefly V-near satellites, which are already created and just awaiting launch. And then shortly after that, at the start of next year, we're going to be sending up another demo sat that's going to be a SWIR satellite. And then following that, we're going to send up our final constellation that's going to be the full vSWIR range, and that will complete out our constellation. And all of these will already, at the end of this year, allow us to reach that daily cadence global coverage, but it will just continue to expand from V-near to vSWIR going into next year. Next slide, please. So when we talk about the current state of remote sensing in agriculture, I'm sure most of you are already aware of all of the different applications and the different methods of acquiring remote sensing for agriculture. Some of the most basic ones that we've seen, obviously, is satellite data. And we know the advantages of this, similar to all satellite data. It's really scalable, capture large areas, capture them pretty consistently. But it does also have some drawbacks to it. And what we've seen, which kind of led to the creation of Pixxel, is that there's always been a low spectral detail. And they have gotten very good spatially, but kind of spectrally, they've always been lacking. Also, for pretty much all satellites, the cloud coverage is always a factor there, but having this ability to create high temporal frequency, so daily imaging, is how we've been able and how other satellite companies have been able to kind of combat that issue. There's also been fixed wing and helicopters for other remote sensing other remote sensing as well for agriculture. And this will give you things like basic field analysis, high resolution analysis, and things like LiDAR for biomass. And these have a lot of benefits to them as well. Very, very high resolution. You're flying at a very low height. So this is allowing you to get image that looks very clear to the naked eye. And you're also able to bypass a lot of the clouds because of this altitude. Some of the drawbacks to this are it becomes very expensive. As you can imagine, having to fly a plane, fly a helicopter, get the permitting for it, get somebody to actually fly it, fuel the airplanes or helicopters. And obviously, it's not something that you can do very frequently. So it becomes a very tedious and expensive way to capture imagery of your areas for agriculture. One of the other methods that people have used are drones, and these have accelerated tremendously over the last few years, creating very, very high resolution. They've actually gotten much cheaper than before, but again, it's still site specific. So it's difficult to kind of draw out that application for very large scale projects, especially if you're not near those areas or they're areas that might not be yours that you're trying to monitor. Again, drones become very inaccessible to that, but they are a very pivotal part of remote sensing in agriculture currently. Next slide, please. So when we start to talk about what makes hyperspectral so special, we have to kind of talk about what makes it different from what's currently available. So on this next slide, we'll see hyperspectral is essentially looking at the visible light spectrum, but through much more bands. So when we talk about bands, we have to understand that it depends on the imagery you're looking at. So if we're looking at RGB, there's obviously 3 bands that we're looking at it: red, green, and blue. When we start to look at multispectral, it starts to go up to possibly 10 bands, like something we'll see with Sentinel. But then once we look at hyperspectral, we start to look into the hundreds of bands. So like when just looking at the visible light spectrum, we might look at certain types of plants, certain types of trees. And when we start to look at it through hyperspectral, we start to apply these very narrow bands that start to pick out different characteristics within different wavelengths of the spectrum. And this is something that wasn't able to be done before with multispectral or with RGB imagery, because they didn't utilize those narrow bands. So that's pretty much what we're going to be talking about today, is how hyperspectral, with the use of this narrowband indices, allows us to go into use cases that weren't previously applicable for satellite imagery, and were use cases that could be done at a much smaller scale with some more expensive options in the past. Next slide, please. So when we're talking about kind of the advantages of hyperspectral in agriculture, it's pretty obvious kind of how it starts to benefit when you're able to create a much more affordable option that has all these advantages. So some of these advantages that we look at through our hyperspectral satellites are species and subspecies classifications. We've seen much higher levels of accuracy when doing this, and this essentially makes the rest of the projects or the rest of the goals that the company has much easier to achieve when you have this higher level of accuracy. And again, the reason that we're able to determine a higher level of accuracy of the species and subspecies is because we're looking at these images with very narrow bands that allows us to kind of place these different types of characteristics to identify what are certain plants and what are other types of species within that plant. Additionally, we can look at early signs of stress within crops or any type of vegetation, and this allows you to kind of proactively remedy whatever's going on. And it's because we're not only looking at changes in the color of the plant, but we're actually looking at changes in the chlorophyll or the carotenoids within the plant. So the plant may not be visibly changing to you, but to the satellites, when looked at it through hyperspectral, you actually are starting to see differences in the spectral fidelity and the spectral response from those plants. And that leads us into kind of the third point of overall crop health. So because, again, we're looking at more than just the visible changes in the crops or the vegetation, you can very accurately and very timely monitor any changes that occur in the health of your crops. So that's pretty much what we're going to be diving into today, a little bit more technically of how all of these advantages can be applied with our hyperspectral technology. Next slide, please. So these are the common use cases that we have begun looking at with our early adopters and our partners. And the main ones that we're going to be looking at today, excuse me, are going to be vegetation monitoring and crop variety identification. And we will touch a little bit on water quality as well. So with that, I will pass it over to Megan, our senior solutions engineer.
All right, thank you very much, Jimmy. So we're going to continue sort of the value of hyperspectral before we jump directly into those use cases, because it's good to build up this sort of base of understanding of the real differentiation hyperspectral data can give, especially when we're talking about vegetation and agriculture. So to narrow in on some of those details that cause it to be so effective, we're going to take a look at the spectra, the spectral responses, and some of the differences between the indices that we have for systems that are multispectral and systems that are hyperspectral. And I just want to point out that as we're talking about some of these upcoming ideas for agriculture, there is a lot more than what I'm going to show today. Today, we're going to be focusing a lot on the vegetation, but that doesn't mean these kind of things cannot be applied to soil, to moisture, to water, to runoff, to so many different parts of the agricultural process. So as we're going through these use cases and examples, just keep your minds open. And if something in there starts like, oh, maybe I could try this, you probably can. So let's get started. So hyperspectral's narrow bands allow us an unprecedented refinement of different surface coverings, from different species and even subspecies of vegetation to differentiation of urban structures, and even the ability to differentiate soil types, nutrients, and moisture content. So what we see here is a pixel image over California. We'll get a little bit of a deeper dive into this image in just a few slides. But what we have here is some points of interest, some spectral responses in this image itself. You can see things such as the bright building roofs in the urban area, the bare soil of near the mountainsides, and the different kinds of vegetation without even knowing what they are, but already getting different signal responses because of the amount of bands that exist there. And so with this kind of definition and information, we can go much deeper into the actual details of what we're looking at from space, which is pretty fantastic. And you guys have probably seen these kind of things before, more with those broadband multispectral indices. So let's talk about those a little bit, because what does that term even mean? Well, a broadband index is a mathematical equation that uses the multispectral or broad bands. And they're called broad because they cover a lot of a different color area, as we saw on that slide that Jimmy showed. They cover a lot of green, they cover a lot of red, they cover a lot of blue. And so they were, naturally called broadband indices. And these are the most common things that are used nowadays for monitoring vegetation. I'm guessing most of you guys in this chat have heard of the term NDVI, or Normalized Difference Vegetation Index, which is a scaling of green that is commonly used to find sort of the health of a plant. So with these, we can get this sort of more information on the ground surface and can use that to get this understanding of an area to a degree. Because they are broad bands, they have broad definitions, and this can cover a lot of information, which can sort of muddle it a little bit and give us good enough approximations. But when we're trying to get into the finer details of what exactly is happening, it's not able to really get into that. So then, let's take a look at what those areas cover. So we're going to zoom in on those important features that are sort of averaged out in the broadband response. Green, red edge, and near infrared are the common multispectral bands used to look at vegetation, and blue and near infrared and beyond are used to highlight moisture content. But each of those broad bands can be narrowed down to specific bands that interact directly with the different physical and chemical responses. So let's take a look at this chart. In blue, we have information such as leaf water content, chlorophyll A and B, that can give us a lot of information on the health of the plant and the moisture that's going on there. In green, obviously a very big one for looking at plant health, we have information on leaf nitrogen, pigmentation, and total chlorophyll as well. And this is where, we get a lot of our information on the chlorophyll content response because it's the pigment that makes it green. When we get to red, once again, a very popular one for vegetation, chlorophyll absorption, and biophysical quantities and yield, such as leaf area index, which is another broadband indice that you guys have probably used in the past. Red edge is exceptionally popular, especially with the increase of drones and as well as satellites that introduce the red edge bands to get vegetation stress and chlorophyll, and is very commonly used to see just how stressed something is. In near infrared, we have biophysical quantities and yield, as well as moisture and biomass as we start going further and further along the wavelengths. And lastly, once we get beyond that, we're getting into a lot more of the biophysical quantities, moisture, and water sensitivity. So we have all these very specific areas, these very well-known, well-documented, there is so much research done, narrow bands that can really highlight these physical and chemical properties that is just really hard to get down to these finer grain of details with other systems. So of course, in response, there are narrowband indices. As sort of stated in the title of these, narrowband indices are made specifically for the narrow bands of hyperspectral data. We're very good at naming things. And so with these, we can highlight these very specific physical and chemical changes. Things like a small change in alpha and beta carotene versus chlorophyll, and can really get into the kind of stressors that can be occurring in a plant related down to the kind of disease or pest that might be in that area based upon what it's doing to the vegetated surface. An example of one of my favorite one of these is called the Plant Senescence Reflectance Index. And we're going to see an image of this later. But the reason why it is one of my favorites is it's actually a sort of balance in between alpha and beta carotene and chlorophyll. And it has an actual numeric scale that means something, which if you've worked with indices before, that's a pretty awesome thing to work with. So with that background done, let's jump into some use cases. So the use cases we're going to be looking at, we'll be using our Pixxel Pathfinder or tech demos, as Jimmy said earlier. And this was one of our collects from the past year. And we're going to go do a little exploration and see what we can see here. So this image, I told you it'd come back, is the image over Stockton, California. This is a bottom of atmosphere reflectance, or level 2A. The date of image capture was July 8th, 2023, so right in the middle of the summer growing season, Stockton, California. And it has 67 bands and a spatial resolution of about 30 meters. So this is one of our tech demonstrators, and as we move forward into the constellation, this resolution will only be increased as we are aiming for, and will be at that 5-meter resolution. Let's talk about Stockton, California for a moment. So the Central Valley is where Stockton is located, is a very large part of California. That's where a lot of crops are grown, for good or for bad, depending upon the fact that it's technically a desert, but this is one of the richest areas of crop growth in the United States. There are over 250 different kinds of crops that are grown in this area, from things like orchards to vineyards to rice to corn to wheat to almonds to whatever you can think of is probably grown in this area. Sunflowers, I think, is a major export from here too. It supplies 8% of the US agricultural outputs and produces about 1/4 of the food, including 40% of the fruits, nuts, and other table foods. And related to the desert, this area also uses a lot of water. So 20% of the groundwater demand is supplied from pumping the Central Valley aquifers, making it the second most pumped aquifer system in the United States. So beyond just looking at the vegetation and agriculture here, understanding the water quality, content, and runoff is exceptionally important to actually get, what's happening in this kind of area. So with that, let's jump into our first use case. Crop species identification and management. So as I said earlier, this area has a lot of different orchards, and trees, as they're growing and as they're growing and as they're in these stands, can look pretty similar even with multispectral data. In fact, tree species classification is one of the more messy classification techniques when you're using multispectral. That's because trees, when they're in their growth patterns in certain areas, they can look very similar. They're pretty green, hopefully. And so with that, we can actually get into the details of the tree species classification. For this example, we're going to be looking at pears, walnuts, and cherries, and you're able to see already an overview map of what that classification looked like, but I will get into the details of the classification, so it's not just showing you a pretty picture. The one thing I really want to talk about here, though, with agriculture, commonly, time series analysis is necessary to get crop species classification, because you need to see the growth stages over time to actually get that higher accuracy that's needed for those classifications, but that's not as necessary with hyperspectral data. If you're able to get it during the right growing period, during a growing period, not when everything is maybe dead and dying off, you can get that spectral differentiation that can actually change it so you don't need as many images over an area to get a classification schema. Instead, you might just need one, as we can see here. So what we used for the background of this one is the USDA puts out crop maps every year. And for this one, we use the USDA crop map of 2022 because these are orchards that don't change too much. Don't worry, I did go through and check if all the orchards were still there and cleaned up some of the sample data a little bit. 30% of that USDA crop map training data was randomized and used as a sort of the base for the classification. In this case, just a simple maximum likelihood classification was used because it helped sort of cover some of the more broad range of the tree responses we could get. Things like random forest were also tested, some specific hyperspectral ones were as well, and they also did pretty well. But we wanted to keep this one simple to just see how it would do with some base techniques, and feel free to ask about those later in the questions because there's a lot to say about them. After that, a classification aggregation, so a post-classification technique to clean up some of the extraneous speckle was used, and then 70% of the ground truth was used for classification accuracy results. And as we can see here, the pixel imagery classification overall accuracy was about 90%, which is fantastic from one 30-meter image. In comparison, not included on this slide, we actually did the same exact process with Landsat because it was also 30-meter imagery, and it got a 24.9% accuracy. So there was a significant difference between the multispectral classification response and the hyperspectral classification response. And we can see in this lovely image here, I took a picture of only walnuts, but we're able to get that kind of differentiation with just one image. But these are just, these are trees, they're there every year. What if we want to get into more details? Because one of the biggest things of understanding is more on the classification of things like cash crops. So corn, soybeans, wheat, barley, on and on and on and on. These are the ones that are of great interest for people, especially when these are being grown in faraway areas that we want to get an understanding of how much soybean is being grown, how much corn is being grown, what's the yield of the wheat in this area, or what are these fields actually focused on for the year. So with that, we're going to move more into the annual style plants and vegetation. These are ones that can change year to year-ish, maybe rice fields. You probably don't want to change those too much just based upon the kind of rice that they're growing. But we're going to take a look at the classification of these as well. So this one used the USDA crop map for 2023, of course, because these crops change year for year and in some areas even season per season. And similarly to the last one, 30% of a random training sample was used using the maximum likelihood classification with classification aggregation to clean it up. And then 70% of the ground truth was used for classification accuracy results. And as you can see here, the Pixxel overall classification accuracy was 91%. Now, we do actually have, and this is between rice and corn in this case. What's interesting is this one was also applied to Landsat. And as you can see the differentiation between the two images here, we have the Pixxel classification overall accuracy of about 91%, and the Landsat classification overall accuracy at 65%, which is pretty good. And the big difference here is the rice. So because of the water content in the rice area, the Landsat near-infrared and SWIR bands were able to get more of that moisture response. When Pixxel has the full V-near SWIR demo, I have no doubt it'll do even better for the separation of these crops. So with that, next we're going to move into my favorite, the plant senescence reflectance index, because let's talk about health. We've talked about classification, and that's a very powerful technique to use for remote sensing, but the one that is commonly used over time series, actually knowing when stress is happening, is monitoring of health and finding the easiest ways to do that are actually useful. So this is where when you're using multispectral, you're commonly using NDVI or maybe leaf area index or one of those techniques, but they're sort of averaging. They're giving you greenness. They're not giving you an actual response, not a physical or chemical property. Maybe it's green, maybe there's brown dirt underneath that's making it less green. And there's also some other factors that can occur too, such as a lot of those indices might have things such as NDVI can oversaturate in super green areas, or it's not the best scaled for soil. So there's all these little finagling things that can make it so you need more refined details on what's actually happening to the vegetation. In this case, the plant senescence reflectance index is an example of one of those. As I said earlier, this is a balance of alpha and beta carotene versus chlorophyll, looking at those changes in the chemical pigmentation of the plants. And the exceptional powerful thing here is that scale on the bottom left, which actually means something. 0 is a non-stressed chilling plant. It's just happy to be here. 0.35 is a stressed, senescing, ripening, or blooming plant. This means it is in the stages where the alpha and beta carotene are giving more of a response than the chlorophyll. And for this example, we're actually looking at some vineyards over Stockton. You can see a lot of them are in this blue to green range. Some of them, the entire field is yellow. Those are fallow fields. It's just soil there. They're getting just a failed response there, or dried plants for the year, depending on how they're going. And then we also get some intermittent mixes of these areas where we have the blues and greens and then go all the way to the reds. So let's take a look at one of those. With the canopy health monitoring, we're able to get into the finer details of these actual responses. In this one field, if you can sort of zoom in a little bit, you can see in the top right-hand side, we have these areas of that bright blue response, and the area is sort of in the middle there of a sort of more reddish orange response, meaning there's one specific area that's sort of stressed or senescing or ripening early, which would be something that you definitely want to keep an eye on when you're looking at vineyards. And we also have a spectral chart here that is showing information on the healthy grapes, which are, as you can see, lower in the visible and near infrared, which is a healthy vegetation response, and then much higher in the near infrared, which is what you want to see and why the red edge is so important. And then the senescing grapes are higher in the visible and near infrared, and then lower in the near infrared itself. or visible, higher in the visible, lower in the near infrared. And so these responses can get us information on what exactly is happening to those crops and make systems that highlight these areas where we're getting these major changes that occur. So though I have been talking about Stockton, California this entire time, I don't want you to think that this is the only kind of place this hyperspectral works for. Those are pretty uniform fields. Most of them are one singular kind of crop sometimes. Some of them can be mixed crop, but it's a very uniform and well-studied area. But all the techniques that were used today can also work in a lot of different areas as well. So an example of this is sort of mixed crops. So you have maybe multiple crops growing in the same kind of area, if it's not like a standard farm like the one shown in Stockton. And you can actually do an analysis called sub-pixel analysis with hyperspectral. I won't get into the details here. Message us if you want to hear more. But pretty much it allows you to understand the volume of these different things inside of a pixel itself. So you can actually see like how much of this is one thing, how much of this is another. Are there different responses in these pixels that could give you an understanding of what's actually growing there? As well as taking a look at crops in irregular and forested areas is a very large, portion of the Earth's surface as well. So because we're able to get that species and subspecies classification down so well, for separating out different kinds of green is very easy and highly accurate. And then you can get into those more irregular style crop plots and get the classifications, get the health studies, and not worry about some of the extraneous vegetation around it. While we're here, of course, we can also talk about soil responses. So soil with hyperspectral depends on if you can see the soil. You can do subpixel analysis to get sort of around the plants, but if you're trying to get an understanding of the soil itself, you want areas that have a little bit of dirt that's able to show to the sensors. But you can get information on it, the different kinds of soil, starting impacts of nutrient content from the soil to the plant. These are all areas where we now have the capability to really study it and move forward and see just how fine detail we can get into, which is very exciting. And then we have moisture content. So as stated in the beginning, a lot of the stuff we're going over today is all sort of based upon the moisture content as well as the water that affects these areas of agriculture. So finding out and seeing, how are these plants doing? How is the soil doing? What's going on here is a very important step when we're working with the hyperspectral data and just agriculture in general. So with that, with the soil content, with the plants, we are able to get that moisture content and make sure things are going properly, like that sprinkler in the middle that decided not to work. And you want to make sure you catch that as early as possible to make sure things are going well. And with that, there's also just sort of going to talk about this at the end is let's talk about water quality, because one of the major side effects, runoff effects of vegetation is the monitoring of water quality in these areas where they happen. So things that can start causing algal blooms or have just effects of nearby lakes, ponds, and rivers, etc. And trying to understand those kind of effects can also absolutely be done. So there are specific bands, 620, for example, 620 nanometers is actually used to highlight phytoplankton. And you can see these areas where it has the higher concentrations and can look for things like cyanobacteria, which might have been caused by an overload of nitrogen and phosphorus fertilizer that has gone down a river into a lake and is causing not very fun things to happen. But because of that, we can also work on sort of pinpointing that, what kind of fertilizer, where is it coming from? What kind of effect is it having on the areas, and hopefully to catch those kind of things like the algal blooms much earlier than possible and work on better ways of mitigation, because there is a lot of work that's being done on, helping our water systems and trying to make sure that those actually work on larger scales and making sure everything is working properly and people are getting all the right results they want is the way to do it. So with that, I'm actually going to pass it back to Amy, and feel free to, I'll pass it back to Amy. Thank you very much.
Thank you so much, Megan and Jimmy. That was a really nice and concise but informative session. So we'll jump over to the Q&A because the box is getting filled with some nice questions here. So Megan, you already touched on this. Maybe you can expand a bit more. There's a question on soil carbon and soil health. So someone's asking, what about soil carbon and soil health specifically? Specific soil health characteristics, can hyperspectral be used for this? If you can just expand on this point.
Yes, the answer is yes, but it's complicated. We actually have a soil carbon specialist on our team. Like that was a lot of what he worked on. And so we've talked about, soil carbon monitoring and soil health monitoring. And the thing with soil carbon monitoring is that you really need a lot of in situ information to get started because it changes and you really need to get down to that granularity level. So even doing it with ground surveys and even doing it with drones can have, well, you need a lot of work done to get it to work accurately. And so it can be done, but there's going to be a lot of forefront stuff that has to be done for those in situ measurements to relate them to the satellite responses, especially just with the atmosphere in between. So it can be done, but it's going to take a lot of work. But the thing is, even saying that, as we're moving forward with these technologies, just the amount of new science that's occurring and coming out and is available means that maybe in the future we'll be able to find an easier way to do it.
Yeah, thanks for clarifying that.
Just a
go
quick
ahead.
note. I see a bunch of people are raising hands. So if you're either raising hands or trying to write in the chat, please write your questions over in the Q&A, and then we'll answer them in this session. Thanks.
Thanks, Jimmy. Okay, cool. So we can jump to the next question. So this question is asking, is your species recognition limited to crops? Can it also be applied to natural vegetation? If so, do you already offer this as a service, or is it done on a project-by-project basis and involves custom modeling and ground truths?
Yeah, I can answer that one again. So yes, it's not only crops. I just didn't want to include all the forestry stuff and other stuff we've been working on as well. In fact, one of my favorite examples that our team has done was actually subspecies classification of mangroves. So being able to not only classify mangroves, but getting into 3 different subspecies of them and comparing them to the actual truth that was there, which was amazing to see just because I've worked in agriculture and vegetation for a while, and actually being able to get accurate subspecies classification is crazy. And related to the projects, it really depends. So, everyone hates that answer, but you can just get the imagery and do it yourself. There are some basics that will be up on our platform to sort of help people get started. But there's a lot of opportunities on whichever way you want to do it is sort of our goal. Is however you want to get it done, it can get done.
Great, thanks. And just kind of to continue on what you just said, Megan, someone else is asking whether sample imageries are available for testing. So I think this is a good point to kind of plug in the platform and all that.
Yeah, I can answer this one again unless you want to, Jimmy. But yes, there is sample imagery. Feel free to reach out to us, and we can see if we have some imagery over the areas that you're interested in, as well as we can see how we can get the Pixxel pathfinders on it as well. So with that, we also do have the Aurora platform, which will be becoming publicly available fairly soon, and that is where a lot of the imagery is stored and will be going forward. So look forward to it.
Yeah, and to add on to that, thank you, Megan. We have been collecting a lot of imagery with our 3 tech demonstrators. We still are operating 2 of those as well. They still are collecting imagery, and this is something that we are working with our early adopters to prove out these use cases, test our imagery, improve it where we can as well. So if you guys are interested in any archive imagery that we have collected, please reach out to us, and we can try to find an applicable image that might be over a similar area that you're looking for. Or if we don't have something, we can set up a tasking with one of the 2 satellites we still have operational to try to collect the area you're looking for.
Yeah, thank you, Jimmy. And again, I'm linking some questions together because someone's asking how the process is for collecting imagery. Again, they're asking whether it would be project-based tasking or whether it's kind of a continuous image capture. So maybe you can just expand on this to make sure we cover all grounds.
Yes, so our satellites are going to be a tasking-based satellite. So We will have to program them and tell them where to collect and what the cadence will be of that collection. So similar or dissimilarly to some other satellites, they're not going to be always on and always capturing, essentially painting the Earth on a daily basis, but they will be able to collect any image anywhere on the globe at a daily cadence if we do program it in there. And to kind of expand on that, at Pixxel, what our core mission is to provide the best hyperspectral data that we can provide. So I know I saw some questions out there asking about kind of analytics or products or that we're going to offer. What we're trying to do is create the best level 2A bottom of atmosphere analytics ready data for our customers. That being said, we do have a lot of customers that are analytic customers. So there will be down the road, I'm sure, a lot of these product offerings or solutions that come from our imagery, but from our company directly, we're going to be mainly providing the data for people to expand on and to create these use cases or products themselves.
Yeah, thank you, Jimmy. Hopefully this answers a couple of questions that came in on this similar topic. Okay, next question is asking, how does hyperspectral time series analysis work?
I'll take this one because it's time series analysis is my favorite thing in existence.
Sure.
So I did say earlier, that you don't particularly need time series for crop classification. And this, of course, is true if all your crops are identifiable within the same time period. So in that picture that we saw of Stockton, California, that's an area where there's pretty much always crops. So there was usually something on those fields. But if you have crops that are growing during the different times of the year, something different in summer and winter, of course, you're going to need data over that. But the main thing for time series analysis and hyperspectral is related to the crop health, stressors, pests, and disease. So the way time series analysis works usually is we try to make the data as simple as possible. So maybe going from multispectral to one band or a couple bands, and then tracking that band series over time, because the human brain and computer programs have a bit of an issue monitoring every single band over time. If you're trying to sort of compare them all to each other, you can do it. So similarly to what you would do with the multispectral systems, is you can simplify the hyperspectral down to those specific characteristics that might show you, like, this is a specific wheat rust response, this is a specific sort of disease or pest that we're interested in, and you can do those comparisons over time, pixel to pixel, and see if there's those kind of changes. You can as well do this with the full hyperspectral data set from one image to another and see if there's different kinds of changes there. There's a lot of change algorithms, things that look through the images and highlight areas that have either gone up or gone down based upon what you're looking at as well. So there's a lot of different options. The things that are, of course, the most important for time series are everything is atmospherically corrected and everything is correctly on top of each other. So once you got those, you're pretty much good to start messing around.
Thanks again, Megan. Here's a question regarding partnerships. Is Pixxel working in Africa, and what requirements are there in place for a partnership program?
Yeah, I can take that, Amy. So we are working essentially worldwide. We have partners spread out globally already. But if you are interested in becoming a partner of Pixxel, you can go ahead and go on to pixxel.space. And under the contact us, we have a become a reseller tab there with a form that you can go ahead and fill out. This will go over to our partner or reseller team, and they'll reach out to you and kind of go from there.
Thanks a lot. Here's another question. Can we find biomass and yield?
Asking the question. So when it comes to biomass and yield, we can do half of it. So when it comes to biomass and yield, one of the things that is the most, like, there's two different things you need to know: what you're looking at and the volume of what you're looking at. So for what you're looking at, we've got it. Hyperspectral analysis and classification of a species, getting down even to that subspecies accuracy, getting the total canopy cover, done. But for volumetrics, you're going to need a more active sensor, so something like LiDAR or synthetic aperture radar, to actually get into the details of biomass, or even in situ measurements. But, trying to do it all remotely that's the kind of techniques you're going to use, which is something that we're looking at because, once again, that's one of my favorite things to do. So looking at the fusion of LiDAR data to hyperspectral data only increases the accuracy of classification and yield and biomass results. So that's definitely something that's going to become huge moving forward, and very excited to see just how far we can go.
Thanks again. Okay, so we have two questions over here. I think we can kind of group them together and tackle them at the same time. So one question is whether we can find weeds within crops, and the other question is on identifying cover crop mixes.
Sorry, could you repeat the first part of that question again?
Of course. So the first question was on whether we can detect weeds within crops.
Weeds.
So invasive.
Okay, yes.
Yeah.
Yep. So, yes. When I was at the end of talking through the slides, I brought up the example of subpixel analysis. And going to that in more detail is if you have these sort of true spectral responses, like you know exactly what this weed's spectral response looks like, and you know exactly what the crop spectral response looks like, you can use these N members to use this technique to figure out just how much of a pixel is, is it 80% crop and maybe 20% tarp underneath? Is it 80% crop or 20% weed? Stuff like that. So you can get into those finer details, even if you have these larger pixel sizes, to find those volumetrics of these different features there.
Thank you, Megan. And here's another question on how can hyperspectral data be used for agricultural drought analysis or modeling?
Yeah, that's a very important question, especially with, all the changes that have been occurring in the years and probably years to come and just droughts in general. So it really relates to moisture content and stressors. So because we can get into those details of the moisture content of the plants, of the leaves, and then also see the kind of stress factors, like they're known. We know exactly what stress looks like in plants. We can see that in the changes of chlorophyll. We can see that when they start tannins, when the tannins start being a little bit more expressed. So we can see those kind of changes on the chemical level and even get them rather early. So sort of side example of this, it was probably shown in the forestry webinar, was we found that when you're looking at things like bark beetles, it can be very difficult to see from multispectral sensors when they first invade a plant, because there's just some minor chlorophyll changes that occur. And by the time you notice it, it's too late. They've already infected that plant and every other one around it. Similarly, but with hyperspectral, you can actually capture those tiny chlorophyll changes and get the change in stress in that plant. So similarly to looking at pests, looking at water content and stresses from drier environments, as well as that moisture that's there, can be done in a very similar way because we have those narrow details we can use.
Thank you, Megan. Thanks for clarifying that. We have a question on interpreting grassland activities, specifically cattle grazing. The question is asking, so how could hyperspectral imaging help over grasslands?
That's an interesting question. So I've done a lot of my work in shrubland and grassland environments besides the agriculture. And the biggest thing that's a problem there is first classification of species, because in some areas it'll be green for maybe 2 days and then it will be brown for the rest of the year. And that greenness to brownness can cause a lot of issues there. But when we're talking about cattle grazing, so that's interesting because it's a physical factor sort of on the surface caused by animals. So we're not going to be tracking the animals. You might be able to get responses for some things the animals leave behind, but seeing that sort of height and health change, so the health change in particular would be the one to sort of take a look at. And you'd have to sort of separate that out from other things. Is it super hot? Was there something else? Are they plowing fields? But I bet you could get, the more bare soil responses rather than the ones that are sort of the brown and dying grass material that might be above it. So that's a really interesting one. I would very much look forward to see the kind of details you can go into there.
Thanks again, Megan. Here's a question directed to Jimmy, I guess, about when will our commercial data be available from the Firefly satellites?
Thank you, Amy. Yeah, so our Firefly constellation is the 5-meter Veneer satellites that we are launching in October. We're going to send up 3 of those in October, and it should roughly take about 2 months to commission them. So if we're being kind of reserved, we'll probably say by the end of this year, we will have our 5-meter Veneer commercial data available for purchase. But in the meantime, we do still have the 3 tech demos. We have the data from those, and we have new data coming in from 2 of those satellites that is available for customers to continue testing on and tasking for new area collects.
Great, Jimmy. Thank you so much for clarifying that. So with that, I will close off the Q&A session because we're running out of time. You will all be receiving this recording via email within the next week. On the screen right now, you can see some of the upcoming events and webinars that Pixxel will be present at and that we will be hosting. So if you're around World Satellite Business Week, do feel free to reach out to us, come say hi, come learn more about our technology and what we're doing. And we've already mentioned throughout the Q&A session that we are launching our Earth Observation Studio, Aurora, and we will have a webinar coming up on the 1st of August to talk a bit more about this, what it's all about, what capabilities are available. So yeah, feel free to join that. We'll be sharing information via our mailing lists and social medias and all of that. So do feel free to reach out to us. And yeah, I thank you so much, everyone, for joining. And we hope to see you at our next session. Thank you so much. Thanks
Thank you, everybody.
to our speakers, of course.
If you guys come up with any questions that you think of after the fact, please do reach out to us. Go on to our website at pixxel.space. You can email me directly at jimmy@pixxel.space. For any questions, any business inquiries, we're happy to help you guys how we can. And yeah, and we'll be sure to send any updates on constellations or technology that we have coming out in the future. But yeah, thanks again for everybody for joining, and looking forward to speaking to you in the future.
Thanks a lot. Bye.
Thanks,
you.
everybody. Bye.